We were discussing the hockey stick identity, and we were learning how beautiful it is and how it appears in the Pascal's triangle. And in this particular video, we will learn a little bit more about Pascal's triangle, which is actually discovered by an Indian mathematician, Olympiad, and he called it Meru Prasthar. Anyway, Pascal's triangle looks like this, and we talked about it in the previous video, and I will quickly discuss why the elements of the Pascal's triangle, the numbers, they're actually binomial coefficients. There is a very simple way to think about it, and I will create some pictures here. So for the first one, I will create just a star here, which is, you can think of the star as null or no object or emptiness. Okay. In the second line, I will draw one dot. I'll draw one dot. In the third line, I'll draw two dots. But I'll just make sure that these two dots are different. In the third line, I'll draw three dots. But I'll make sure that all the three dots are different. Similarly, four dots, and I'll make sure all the four dots are different. Alright, now what am I doing here? My claim is that each line of the Pascal's triangle tells me how many ways I can choose stuff from the dots, and I'll write that. My goal, so I'll keep this small, my goal is choose dots, and I want to show that each line of Pascal's triangle tells me the number of ways I can do it. So let's look at why. The first one is very easy. The first set of objects is empty, it is null. So if I have a null set, there is only one thing I can do, that is do nothing. Do nothing. And this is just this number 1. It's a very, very powerful idea. Doing nothing is actually something. Think about it. Doing nothing is actually something. It's very different from doing something. So it itself has its existence. And that is the number 1. It represents doing nothing. The number 1 in the first line. Let's look at the second set, which is a single dot. A single dot. So there is only one object. In fact, I can put a little bar at the top of this dot, a little dash. This is just one object. So what can I do? I can choose it, choose this object, or I could, that's only one way that's possible, or I could not choose this object. Not choose this object. So that's the second thing I can do. That can also be done in only one way. So from 1, I could choose 1, or from 1 I could choose none, 0. So from one object, which is this one, I could choose that one object, or from one object I could choose none, or none of them. Like there is only one of them, so I don't choose it. Both of this can be done in one way. So this is the first one is 1 choose 1, and the second one is 1 choose 0. Or you could do it in you could actually flip it. Let's make this first one 1 choose 0 and the second one as 1 choose 1. There is only one way of choosing nothing from this particular set of one object, and that one way I have recorded here. This number 1 represents that one way of doing it. What is that one way? Do nothing. I told you do nothing is actually something. Okay, the second thing is, the second part of the story is choose one object from one object. How many ways can you do it? Well, you can do it in only one way. Choose that object. Choose that object. Things will be much more clearer in the third line. Let's look at the third line. It has two objects, both of them are different. The first number tells you 1 choose 0, the do nothing case. There is only one way to do nothing. Do nothing. Okay. The second number tells you the number of ways of choosing one object. This is 2 choose 0, 2 choose 0. There are two objects. From two objects, choose nothing. The second number is 2 choose 1. Well, there are now two cases. You could either choose the first object, that is the first case, or you could choose the second object. This is the second case. So there are two cases, two ways of choosing one object from the two objects that we have. And the third case is to choose, maybe I can write it, to choose 2. So choose both of the objects. There is only one way to do that. Choose both of them. That's it. Okay, so do you see what I'm doing here? You can run this same logic in the third line. This is 3 choose 0, the do nothing case. 3 choose 1. Well, choosing one object, you can either choose the first one, or you could choose the second one, or you could choose the third one. There are three ways of doing 3 choose 1, so that's why the number is 3. This is 3 choose 2. So you could either do first one and first two objects. You can select two of them, first two, or you could select first and the last one, or you could select second and the last one. And this one tells you 3 choose 3. 3 choose 3. Because there is only one way of selecting all three objects. Do you see what I'm doing here? I'm converting each of the numbers into the number of ways of selecting objects. So now how does this look like? The Pascal's triangle now looks like 0 choose 0. Maybe I can write it like this. 0 choose 0, because you're doing the null case. Then we have 1 choose 1. 1 choose 0, 1 choose 1. Then we have 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So the Pascal's triangle is like this. This is the do nothing case. So this is 1. This is choose nothing, one way. Choose everything, one way. Choose nothing, one way. Choose one at a time, 2 ways. Choose all of them, one way. Choose nothing, one way. Choose one at a time, 3 ways. Choose 2 at a time, 3 ways. And choose everything, one way. The Pascal's triangle, each of these numbers are the number of ways of choosing objects. And it's very important to appreciate the discovery of the fact that doing nothing is actually something, or rather is one thing. So that's here. Doing nothing is one thing. I'm recording this video in the age of corona pandemic. Remember, if you are at home and if you are doing nothing, then actually you are doing something, that is, you are saving lives. It's a very practical example of the case where doing nothing actually counts. Okay, so remember, we were studying hockey stick identity, and somehow this is my hockey stick. What I am saying is 1 choose 1 plus 2 choose 1 is equal to 3 choose 2. This is my identity. Why is this identity true combinatorially speaking? In the hockey stick identity, why is this true? Can you generalize this now for in the Pascal's triangle? Make sure that you are using these binomial coefficients. You're using this choosing of objects technique to frame an equation that represents the hockey stick identity. All right, keep on doing great mathematics. I'll see you in the next one.